So I think we can start now. So good afternoon, welcome everybody. Most of you were here this morning, so I am not going to repeat the introduction I made about Bjarne Stroustrup. Anyway, if you are here, you probably know him. So, but let me take a couple of minutes just to say other things that we are doing in a couple of months here, just in case you are interested, around C++. Every year, except last year, we have a one-day conference here at the university about C++. This year is going to be our 6th year having a C++ conference. Is a one-day event. It's a free event. You only need to register to come. And we are making some slight change this year. So this year we decided that most of the talks are going to be in English because we have several international speakers, but also we decided that many of the talks from Spanish speakers are going to be also in English. We'll see how the experiment works, but we think also that is fair for people making the effort to prepare a talk that is going to be recorded, to record it in English and to put it in YouTube so that it can be used by more people. Still, we will have some talks in Spanish. These are some of the speakers that we will have. We will have Arno Schodel. Probably some of you know him. He owns a company in Germany quite involved in C++ and in the C++ standardization process. We have somebody from the Qt company. We have Guy Davidson from Creative Assembly. I knew yesterday that the same day Guy will be here is the day they are launching the next video game in the Total War series. And he's going to talk about linear algebra and video games. We have Jose from Belneo. He has been here several years. Martin Knobloch from InDesign. Axel Neumann from CERN will be talking about reflection. Javier Sobo from Conan. Juan P. Bolivar is an independent consultant in Germany, in Berlin. We have somebody from an astrophysics institute, and Joaquin Lopez, another independent developer. So I think the program is attractive. If you are interested in C++, we will be happy to have you here on March the 7th. Anyway, I see a lot of familiar faces, so it will not be your first time here. These are our supporters. InDesign company is our gold sponsor, and we have two silver sponsors, Conan and SyncCell, and the cooperation of JetBrains. But today, as I said this morning, we are here to celebrate the honorary doctorate given to Bjarne Stroustrup tomorrow by our university. This is something that makes me really happy. I think it's a great achievement, and also I think it's one of the ways we had to say, Bjarne, thank you for giving us the C++ programming language and for all the contributions he has made. And well, you know him. I was joking this morning about he has the bronze, silver, and gold medal. He has the Faraday medal. He has the Stark Draper medal from Academy of Engineering in the US. He got very recently the IEEE Pioneer in Computing, and many more awards much more important than the honorary doctorate that we are giving him today. So it's for me a pleasure to ask Bjarne to go for the second talk today, which is probably much more detailed than the one you got in the morning, and I think it's also a good continuation of the one we got in the morning. So, Bjarne, thank you very much.
Yes, thank you. We definitely that. Okay, thank you. Thank you for coming. I'm feeling very relaxed after a good Spanish lunch. So we'll blame any problems with this talk on good Spanish lunches. I'm going to talk about concepts and generic programming. And I'm not going to say that many technical details about concepts, because I've been working on them for a long time, and I'm now thinking about how do you use them well. So basically, I'm going to talk about generic programming and what are we trying to do and what are the really fundamental parts there. And then I'm going to say a little bit about how you use concepts to gain some benefits. And then towards the end, I'm going to say what a concept is, sort of from a language technical point of view, but this is not a language technical talk. It is an attempt to explain what we're trying to do and how to get there. And then a little bit more detail if we get that far. So basically, if you go back, Mossa and Stefanov, especially Stefanov, defined generic programming as we've been doing it in C++ for a while, and he's focusing on algorithms, which is one of the things that are different from sort of people talking about object-oriented programming and such. Basically, you take a concrete algorithm and you abstract it by making its requirements explicit, so that you can see which kind of structures you can apply it to. That's the fundamental idea. So if I have an algorithm that works on integers, can it work with floating point numbers? Can it work on big numbers? How about complex numbers? How about matrices? In many cases, the answer is yes, 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 and yes. And we should be able to write the code that works for numbers with the properties we need for in the same way and as easily as if we did for just the integers. And it generalizes quite dramatic. And my aim for C++ is simply I want to make generic code as simple as non-generic code. In some sense, we have to think really hard about the details of integers to write something that just works for integers. If we instead think about what is really required by the algorithm, by our program, then maybe we can actually get something that is as simple or simpler than if we just used a single concrete type. And if nothing else, we've thought harder about what the requirements are, so maybe we don't mess up with 0 or something like that. It's an unusual case, or written the algorithm so that it forgot about negative numbers, or something like that happens. And it's not just the foundation libraries. A lot of this goes into application code. And basically, my buzzword here, generic programming, is just programming. There's nothing just about programming, of course. It's a fairly noble art. But basically, I want to dramatically affect the way we design things and improve the design. I'm pretty sure we'll get there. So The aim here is better code, cleaner, simpler, more readable, more maintainable, faster, less clever, more general, type safe. This is a really nice list of things, and I think we should agree that we want to go there, and I'm going to show some examples of where we can go there. Concepts doesn't solve all your problems. As I often say, if you don't have good ideas, no language will really help you, because you just write the bad ideas down. But if you have good ideas, it should be fairly simple to write them down. And again, I'm not going to talk about parsing or grammar and exact algorithms of things. No. So basically, there's a status here. Concepts, which I'm going to explain later what are, was a technical specification in 2016. They've been shipping in GCC for a couple of years. So if you haven't tried it, well, you could have if you had wanted to. A lot of people have tried them. And we have put concepts into C++20. It's voted in, barring absolute disasters that are unexpected. We're going to have them. For those of you who have seen concepts, the explicit requires clauses are there. The shorthand notation is there. There's a function-like syntax there. We have the ranges library that uses it to be able to deal with ranges in the standard library. So you can now say sort of v instead of sort of v dot begin, comma sort of v dot end, because it will recognize that sort requires something that's sortable, and the range will define what it means to be a range, and it'll figure out that sortable is something you can do to a vector. That'll all be done automatically by the compiler. We have low-level, like assembly code, things required clauses, and we didn't actually manage to get something called concept type name introducers, but tough. Okay, that was for those of you who had been following the standards committee. So basically, going back to in history, the history of generic programming in C++ starts quite a long time ago. I tried to use macros to get generic types. So basically, you start saying, I want a vector of elements with type T, and then you want the sort function of vectors of type T, and then you get sort of the basics of generic programming. First the data types, then the algorithms. Alex always goes first with the algorithms, but a lot of people invent things in this order. And I thought that macros could do the trick. I'm on record for saying that, and I was really wrong. I had the right problem. You wanted to express general things with types and with types and functions parameterized with types, but I just got it wrong. In 87 or thereabouts, I started figuring out what I really wanted, and I wanted something that was extremely general and flexible, must be able to do much more than I can imagine. I explained this in the morning, that if you have a language that can only do what I can imagine, we have a very impoverished language. Not that my imagination is worse than anybody else's, but a larger group of people with different experiences will come up with different problems and solutions. And we wanted zero overhead as a C++. If you can hand code it better, people will. And so we'd lose the notational advantages, the type checking advantages, and basically deteriorate into hacking. So it has to be fast. I wanted to compete with CRA, should be able to build matrices and vectors that runs within a few nanoseconds as well as CRAs. And I wanted well-specified interfaces because, well, you can get good overloading, good error messages, maybe separate compilation, and that I couldn't do. Neither I nor anybody else knew at the time how to do all three. So I picked the two first, and that worked rather well, and so templates got popular, template metaprogramming became popular, generic programming became popular. but it really hurt. Well-specified interfaces is one of the keys to good design. It's one of the key ways of structuring the software so that we can maintain it and we can understand it. And I was falling down on this one. So that's what we had here from 94 thereabouts to now. And now we aim to precisely specify interfaces for generic code. We're using a language construct called concepts, and that of course goes back to the original design. So I've been working on this roughly since 80, more specifically since 87, and we have a TS now, a technical specification, and well, next year we should have it in the standard. We'll have all the compilers doing it, and we can rely on it in our code. I'm looking forward to that. So basically we go for generality, zero overhead, and good interfaces. So let's go back and look at the history a bit. So there is sort of a piece of code that you can find in Kernighan and Ritchie 1. This is the kind of code I was taught when I first came to Bell Labs. You have a function that's a square root function, and if you call it with square root of 2, it crashes, because I didn't tell it that square root takes doubles, and it does. If you can look there, it takes a double. But up here we don't know it, therefore it crashes right here. Or I can say square root of 2 and get another runtime crash. I took one look and said that's unacceptable. And it took 30 years for the C committee to realize it, but it's now don't do that in C. So basically the solution was make this interface correct. If you want a double, say you want a double. That's very, very simple. And just about any language but C could do it at the time. There's nothing really creative about that, except of course no languages that could work in the environment where C worked were particularly good at this. So anyway, now we say square root of 2, we get the correct answer, because we know how to turn a 2 into a double. Fine. And we do not know, and we don't really want to know, how to turn 2 into a double implicitly just because we do a square root to it. If we wanted to, we could do it. You can do anything you like, but this is usually considered a good thing that you get a compile time error. So instead of getting runtime crash, you get this one works and this one is an error as it should be. And this is sort of fairly close to what we want to get ideally. Oh yeah, and I fixed the syntax so that now you can use the same syntax here, and as we use for declaration, we can use it for the definition. Fine. Those of you who have been using C probably can't even remember this stuff, if you've ever seen it. Okay, so this is important. It is easier to read. I can see it takes a double. Maintenance is fine. You can get safe linking and all kinds of good things because you've said what you wanted. It's a fundamental idea of stating intent. The intent is that we take a double. This is the simplest example I've found on this. Okay, fine. So let's see what we are doing with generic programming sort of in the 2000s up to about now. So I have here a sort function that takes something that is a type, and it takes 2 of them and they use it as an iterator. You see, it doesn't say it's an iterator. It says that, well, there's a type. And so I try integer vi, and I try to do this. Yeah, that works. I try to do that with lists, but it does something with its arguments. And you know, somewhere in the manual it says that to be a good argument to sort, you have to be a sequence. The list is a sequence. It has a begin and end. You have to be a list of something with a less than operator. Yeah, list has got that. And you have to have random access. List hasn't got that. boom, you get several pages of error messages that is really hard to see what went wrong. We can get it wrong in other ways. Here is a vector of s's. S's are defined right there. We get an error just as obscure because, well, the committee wouldn't give me default comparisons for structs. So it doesn't have a less than. Boom, crash. Because we couldn't say up here what we really wanted. And we've lived with that for 15 years, and it's a major success, but this is ugly. It's unacceptable. It's unacceptable just like that, which was also successful for maybe 30 years, but it just makes programmers suffer unnecessarily. Okay, I could even have called sort with 1, 2, because it just says it wanted a type. Int is a type, 1 is an int, 2 is an int, so sort of 1, 2. The compiler would say, yeah, that's fine, till it gets to template instantiation and it blows up. Okay, we can't do that. So the templates was a massive success. They're flexible, they're type safe, they handle specialization, they give really good runtime compilation, runtime speed, because you move work till runtime and allows you to craft exactly solutions exactly matching your requirements. This is great. And there's problems here. Verbose syntax, doc typing, error messages, very clumsy overloading because we haven't stated intent. Okay, so what do we do about it? First of all, if we can say what we want, there's a chance we can get further. So here, sort should say they want something sortable. That auto there was put in by the standards committee because they panicked when they couldn't see that sort of sortable was a template. I don't see why you should know it's a template. I want ordinary programming and generic programming to look as similar as possible. But basically, so this says sort is a template that takes something that's sortable. That's not bad. So I can sort the vector, it's fine. I can sort the list, no, but you get the error message at the point of call that says, no, it's not sortable because it has no subscript. And I can say sort of VS, it says it's not sortable because the value type, the element type, doesn't have a less than. So that's sort of the first level of utility of the fact that I said what I wanted. Sort requires something to be sortable, and later I'll show you how to define sortable. It says so in the standard, of course, and compilers don't read standards. It will, however, for CEN 20, read things like that. Okay, preliminary has been shipping for more than 2 years. This is not science fiction. So anyway, so here, to beat overloading, in the standard we have roughly this. It's done differently, but basically you could say sortable that gets a container sorts by using the beginner and the end. That's fairly easy. Since it's sortable, we know it's a sequence. A sequence has beginner and end, so if we give it an integer or something up as an argument, it will not even get to look in here. It'll find the error there. Now, if I also want to be able to sort lists, which the standard doesn't allow, but if I wanted that, I'll simply say, well, I'll define a list type, a list concept. So here is a template that takes a list, and a list will be defined as something which is a sequence with a comparison operator, but unfortunately it does not have, we were not requiring random access. And now I can write list here, it's easy. You initialize a vector with the container, then you sort it, because we know how to sort a vector, and then we copy it back again. Fine. And now we get okay, okay, and we still get an error here because it's neither a list nor a sortable. That's fine. Just say what you want. And there's been lots of debates about concepts and types. And this is the kind of thing that you can write long papers to learned conferences about. been there, I've done that, got the t-shirt. So yes, I can do that. I can, if I absolutely have to, write with Greek letters, but I'm not going to do it here. That's not that kind of talk. And so basically a type specifies the operations that can be applied to an object, implicitly or explicitly. It relies on function declarations and language rules to enforce this, and it specifies how an object is laid out in memory. That's roughly what a type is. How can you make a value, what operations do you have on it, and what does it look like in memory? A concept, on the other hand, specifies the set of operations that can be applied to an object, yes. Implicitly and explicitly, yes. It is defined in terms of use patterns, I'll show you later. That is a way of representing language or rules to the thing. It says nothing about the layout of an object. So the way I think of a concept is it is something that says how you can use something of the type, but you can't make them. It is simply about usage. And that is the major distinction here. And that makes this far, far more general than that. I mean, if you have a double, it'll say how much space a double takes. If you have a matrix, it'll say how a matrix is allocated. But I can use this. If I only use plus, I don't care how it's allocated. So this is how you abstract from details that you don't want to know. In particular, most of the implementation details are abstracted away right here. Okay, let's get further. Let's see an example here. Here is the first concept. The concept is an integer, which I define to be the same as an integer and an int. So the type a thing is an integer. A type t is an integer if it is the same type as int. You can't get more simple than that, right? I'm not generalizing yet. I'm just expressing ideas using concepts. And now I can do things like give me an integer, right? Give me an integer. I can actually also say give me an integer which is the type is deduced from these. Those of you who uses auto know that I could write auto x1 plus x2. It would deduce the type. Here, it deduces the type and then it checks that it's an integer. What's an integer? Well, it's an int here. It's very simple. I can write the integer. It just works. So this is an idea of showing how close types and concepts really are. And here I have two functions. One takes an integer, and one is a template that takes an integer. Since an integer really is an int, we should be able to use these two exactly in the same way. And we can. There was the x and y up here. And so when I'm talking about making generic code similar to ordinary code, I'm not kidding. Here you can't actually tell till you look at this that it was a generic type. Okay, so this, by the way, is Andrew Sutton, who used to work with me in Texas. He's now a professor in Ohio. He worked a lot with the implementation and the design with me, and he implemented it. If you have used concepts in GCC, you can thank Andrew. So basically, we want to support good design. We're heading for reliability, maintainability, and overloading so that we don't have to do all kinds of magic for types. It's just the usual rules. And here's the comment about, well, I'm trying to do something very similar to C++ that I was doing to C by adding the ability to specify the requirements of a function. Okay, so here, what have we got? Advance, one of the standard functions that you may have seen. It takes a forward iterator, a reference to a forward iterator, and a reference to a random access iterator. This is the advance that goes slowly towards the end steps. And this is the fast one. If you have random access, you go to the end. So one of the real keys in generic programming is the ability to distinguish when you call on one kind of type versus another kind of type. You're using it every day if you use the standard library. It's just here, it's said explicitly. If you have a forward iterator, go slowly. If you have a random access iterator, just jump to the answer. This is where you get sort of the order of magnitude advantages. That is O(n), this is O1. And so now, if I have a vector of strings and a list of strings, and I want to advance the vector of strings with 2, I use the fast one. It basically asked if it's a random access iterator, and the answer is yes. Here, it also asked if it's a random access iterator. The answer is no, so you use the slow version. And fast and slow, of course, is not known to the compiler, but the compiler knows about more or less constraint. And the rules is that you use the version that is the most constrained. So that if you add requirements, you should get better things added. And this is the least requirement, so you use it if you have to. And we compute these things. There's no statement anywhere that says this thing is derived from that and things. This thing is important because this is what makes it different from object-oriented programming, where you have to predefine hierarchies and gets constrained by the fact that you can only be in a hierarchy in certain ways, and you have to you have to choose in advance what kind of algorithms you can call. Here we just look at the properties and pick the right one. This is quite important. So basically it simplifies the side overloading and conditional properties. If you've used enable if, you'll know it's easy to get into a mess. I don't particularly like enable if, and I won't even pronounce what it takes to get this working. But basically, lots of detailed code, just a lot of detailed metaprogramming, simply get replaced by saying what concepts do you require, and let the compiler compute what is the best answer. Like that. It just looks at the code, look at what you require, and pick the right one. This is remarkably simple and remarkably effective. I mean, it doesn't solve every problem on Earth, but it just solves most of the simpler ones, which are the most common ones. And so, surprisingly enough, concepts improve compile times. That is, it catches errors earlier, but also you don't have to go through the workaround people are doing. And so basically we find that the compilations speed up, and we catch errors earlier, and so we don't have to have so many compiles, but individual compiles have been known to speed up compared to workarounds. Andrew Sutton did a fair number of experiments with that, and there are 2 versions of the range library. The range library is the new algorithms library for C++20 that gives you infinite ranges and ranges defined as beginning and n elements and things like that. Good stuff. There are 2 versions, 2 implementations that's been maintained for the last 2 years. One using old-fashioned techniques and one using concepts. The concept version compiles 30% faster. I know I usually prefer factors, but adding a language feature and then having things run 30% faster, compiling 30% faster, is good. I emphasize that because in the notes for C++ OX, we had some concepts that I mentioned. There's a miserable failure, and one of the reasons it's a miserable failure was that sometimes you got 3 or 20 times slower compiles. That's not acceptable. I much better like a small improvement in compile speeds. Okay, so that's important. I mean, all of this has practical aspects. There's a sort of an engineering aspect to it. How do you tweak the ideas so that you can actually implement them well? Okay, so I'll just show you, since not all of you could have imagined how to use enable if you hadn't seen it before, but there are people who like them, so I'm going to say what I don't like about them. So here is something that actually we want to do a lot. I would like to have a smart pointer class, and I want to give it a dereference operator, but only if it's a class. Because if it is a point to an integer, of course I shouldn't have an arrow operator. So if you look at the standard and the implementation of the standard library, that's one of these. And I can say it very simple. I want an operator arrow, and it requires that T is a class. T is a class is something that's defined in a standard library. It's a type trait. Its compiler will give me the answer. So basically, give me one of those if it's a class. That's not brain surgery. I mean, that's just what it is. Now, we can also do a class pair. Should have a, let's see, what have we got? What am I trying to do here? Oh, we should be able to build a pair of T of U from a TT and a UU if and only if I can convert a TT to a T and a UU to a U. That makes a lot of sense, and it says so in the standard, and you can go and look at the implementation. It is hair-raising. I'm not even going to show it. But here, we simply say that we can convert a TT to a T, and we can convert a UU to a U. If and only if this is true, will this class get the pair constructor. There. Again, say what you want, and you get it. Let's see, do I show a bad example? Yeah, I show a bad example here. I show the simplest thing I could find, which was I want the arrow operator if and only if U is a class. And this is not exactly pretty. It means it goes away if it's untrue, otherwise it becomes a T star, that's the return type. And I mean, if you've seen it a million times, it becomes normal, but there's a lot of things that become normal if you see it a million times. This is, I think, ugly, hard to write, hard to explain, and it only works in a few cases. It does not. I mean, don't even try for this one unless you want a headache. And so, two or more predicates are really hard, and sometimes you have to have something is true and something else when it's not true. That's common. And if you have something that is true and not true, and for two arguments you now get four different alternatives that you have to keep track of it. With concepts, you just require it and let the compiler keep track of it. I love it when the compiler can keep track of it for me. So basically, the syntax for this is just yuck. So that's what we want to get rid of. Also, readability is a major issue. Here, every new feature will be misused and overused. I was the one who invented auto, so I'll take credit and blame for it. And it's overused. And here's an observed program, observed problem in real production code. People wrote auto ch foobar of x of y. Ch, as I happen, stands for channel. This happens to be an application to do with networking. And then people write auto ch equals foobar, and then the testing. And we soon find that people can't read this stuff. And we don't know where a bug is caught, because we just deduce it, and sooner or later something goes wrong. But since this is very non-specific, it carries on possibly for a long time. But the main problem is we found developers sitting flipping back and forth to try and remember what foobar did. I have very carefully removed the hints that there aren't real codes by well-chosen names, but people are still flipping backwards and forwards and getting paranoid because they couldn't quite see if it did what it was supposed to do. And response Oh yes, the first response is that they litter their code with comments. And the comments, of course, means there's more to read, and comments are not always correct. So this is what people do pre-concepts after having found the problem with readability of auto. And what we do now, input channel, and well, I can't just get the right input channel there, that pains me, but input channel to be deduced from foobar. And now this code will only work if it really is an input channel, and that's beneficial. The developer can now read what it's supposed to be, and the compiler will actually make sure that it is true. In other words, it says that the result for foobar channel should be able to be used as a input channel, which is all you need to know. I mean, it might be something more than an input channel. There might be the equivalent of a class hierarchy lurking here, or there may be quite a few different types, even unrelated types, that happens to be able to work like an input channel. But we know, at least from now on, we can use CH as an input channel. So this is very classical type checking. It works only if our expectations are met. And why? Well, let's see. Here's another one, classical, that's find. It says, I want a type which I'll call input iterator, and I want a type that's called value, and then it does something. And basically, the syntax here with template, type name, wasn't my first choice. That's very verbose. Why do I have to say template all the time? Why do I have to say type name all the time? We'll get to that. But basically, there was a simpler syntax, and I got yelled down. That was, people were not ready for generic code to look just like ordinary code, and apparently they still are, so I have to litter my code with these autos. Let's see. With concepts, we can actually say I want an input iterator, and I require that we should be able to do equal comparable with the value type of the iterator and the value. So I can specify very precisely what find is supposed to have, as opposed to just say there's a couple of types, and then I use the couple of types and hope it works. Duck typing, right? If it walks like a duck and it quacks, it's a duck, except when it's a rubber ducky or something, and you get strange errors later on. So, and we write the code here, and there's good checking on the, no, that's, yeah. And with auto type name, we must read the implementations to know that. Basically, if I write it this style here, I must either look in the manual or I must read and understand the code to see what the requirements are. Here I state them explicitly. And so, yes, here's the definition. This is actually copied out of the range library. It's going to be standard next year. So I need an input range, and I need the equality comparable, and I do it to a ring and a range and a value, and returns a safe iterator for the range. So this is actually production quality specification of a range. You find anything in anything that is a range, and the range is basically the thing that has a beginning and an end specified somewhere, and the end might actually be infinite. So this is actually a generalization of find, but it's much better specified than it used to be. You can read the declaration. You don't have to look at the implementation. That's true for you as a human and you as a compiler or a tool. That's improvement. Readability. So one of the things that happens when you get a new language or a new language feature or a new library, everybody writes their code the way they used to, and it gets ugly. Sometimes in the dark ages I'd learned Algol, and then I learned Snowball, which is a radically different language. And I found myself, after a few days, writing Algol in Snowball. This is truly horrendous. They are unrelated languages. But people have been trying to write Smalltalk in C++, or Java in C++, or C++ in Lisp or something. It doesn't work. You have to think a little bit about how you use the new set of facilities. You actually have to learn to think in the new language. Another example is that if you start speaking in a foreign language, like if I started to switch into German, you'd probably find I was using Danish sentence structures in German, and it would be patently obvious I didn't know what I was doing. The more different the languages are, the more wrong it is to not use the right idioms and techniques. And so don't expect the initial libraries to get all the benefits that we're promising, because people are going to write bug-compatible libraries. And sometimes that is quite hard. And so when you come, also people are trying to learn from advanced foundation libraries. I can't actually recommend you to learn concepts by looking at the range library, because that is a really nice library that has to be almost compatible with the old ways and is generalizing across more things than most people think about. It's a foundational library, and it has to have optimal performance. So this is the kind of thing that's, well, it's you don't start learning, say, English by reading Shakespeare. That takes a little bit of practice. And similarly for concepts, beware of the first attempt. Your first attempt or anybody else's first attempt, because we need to generalize, we need to find the idioms, and once we can do that, things get much prettier. And I'm saying that with a fair amount of confidence, because people like Andrew Sutton has been doing nothing. Well, that's not true. He's been doing a lot of this over the last many years. I've doing it a lot of over the years. I teach students once a year. They can all do it after a week. It's not hard. On the other hand, people that's been trying to do things thinking the old way has written very ugly code and then complained that their code is ugly. I learned a lesson. I did not complain that Snowball was a bad programming language because my Algol didn't work in it. It was actually a formative experience, somewhere in my first year of programming. Never again, never again. I mean, the first attempt is going to be not quite right. Okay, and so typed versus untyped is the thing that comes up again and again. Auto became very popular after it came in C++ 11 because you don't have to repeat types. I mean, it is really nice to be able to say auto x equals 7 and have the compiler figure out that 7 is an integer, so x is an integer. And even better, auto p equal v dot begin. P is whatever is the iterator type for v. It's even hard to write the iterator type for v because first of all you have to know what it is, and secondly there's template parameters and such. So this became very popular, and as a matter of fact I found out with concepts we could do without auto. Look at this. We have a type is auto if it's true. In other words, for all types will match auto. And now I can write capital auto x equals 7. It'll deduce the type of 7, see it's an integer, see that integer matches true. Of course it is, everything does, and we're home. I could actually eliminate auto using concepts. It's sort of an interesting observation. It shows that something is being coherent here. Anyway, the idea, accept a concept wherever auto is. So whenever I can say deduce this type, I can give a concept and say deduce this type and check that it matches my expectation. Input iterator, number, whatever. And well, it's backwards. We should have expected auto wherever our concept is and use that one, but I don't have my time machine. I can't go back and do this. And a historical factoid is that I proposed auto, f of auto, in 2003. In other words, take an argument, figure out what type it is, use that f as a template with an argument of that type, and you look at what it returns, deduce the return type, and get it out. I've never heard scream so loud in the evolution group as when I proposed that one. And I should add another historical factoid. I invented auto back in the winter of 83, 84, but was forced to take it back out again because one, people were convinced it was useless, and two, there was a slight C incompatibility. So I had to wait 25 years. Okay, sometimes you have to be patient. But anyway, type versus untyped. Types really are useful. They document intended use, they improve readability, they gives us overloading, give us better error messages, and it helps optimize us. That's all good stuff. And overly general types cause problems. So if I see void star in code, I wonder what on earth are they doing? They want to point it to some memory? Yeah, it happens. Sometimes we need to do that, but we'll better hide this behind some properly typed interface. Similarly, template type name T, I want a type. It is very rare I only want a type. At least I would like to have it copyable, or an object type, or an iterator, or a number. The number of times I just want a T is extremely low. It usually relates to template code that manipulates syntax trees. But even there's usually some strict constraints on T. So this is going to be suspicious. If you worry about this in your code, you should start worrying about that in your code. It's the same thing. It is too general. It allows everything to slip through. Especially it allows things you haven't thought of to slip through, to get bugs. And here's auto. Here's a lambda, and it takes an X. What on earth does that code expect of that? For lambdas, if they're small, you have a chance of actually understanding what's going on, but you still have to read the implementation to know what's required. These things are suspect. You didn't say what you really wanted. You just say, let any old stuff come through and see if it works. I don't believe that philosophy. So my expectation is that concepts will change the way we think about programming, design, interfaces, and types. This is going to take years. This is a fairly major thing. This is why I'm excited about concepts. I mean, one of the things I was thinking a long time ago was you really need to change the way people think. That is the aim of language design. Hopefully for the better. But definitely, if people write code the old way, you have not made progress. So this is what we're after. And so concepts is not just business as usual, it's major. Okay, and it takes time, but individuals can do better than the community as a whole. We move forward sort of one step at a time, one person at a time, one program at a time. There's billions of lines of codes out there, there's many millions of programmers. This is not going to happen overnight. And not everybody's going to agree with everything I'm saying, of course, all of these things. But I would like to move. So let's see, what's a concept? That's Alex Stefanov. He's the father of the STL and basically the guy who thought up generic programming as we see it in C++. And he says concepts is all about semantics. The only snag is that there's nothing here that we talk about that is really semantics. It's all syntax. A sequence is something with a beginning and an end, or a beginning and a count. A random access sequence is a sequence that gives me subscripting and plus. But we sort of can approximate semantics by having groups of operations that are supposed to work together. Sometimes we will probably be able to put in actions so that we can actually have real semantic coherence, like specifying we should have to have plus and minus, and they have to have this relation. Then we get into groups, monoid groups, fields, and all of that kind of stuff. We can do that. But it's not supported just now. Bjarne Stroustrup and I designed it for C++ OX, and it'll work, but we can't have it just yet. Anyway, so that's where we're going. So he started in 81, algebraic structures. See, this stuff is pretty old. In 88, I failed to find a way of doing this right. Good try, but I failed. Then 94, we got STL in terms of concepts, but they couldn't be represented in the code, so they're in the comments. So it actually says that find takes a pair of input iterators. But the code is simply two types that are called, one type that is called iterator and two of them. So it moved sort of from the totally, it's comments. It's the pseudocode on the side says what the requirements are, and that's not good enough. So in 2003, Bjarne Stroustrup and I came up with a design that's actually pretty good and is a direct ancestor to what we have today. Group in Indiana, some nice people there, worked on a design based on function signatures. The way a lot of languages do it, they say that a concept is something that have these functions with these argument types. The problem is it's not flexible. We said, well, a concept is something that can do, where you can do this to an operation. So the Texas design says you can add if you can take two values and add them with a plus. Whereas the Indiana design, which is more classical, says the type must have a plus function that takes arguments of these types. The problem is you can't specify those types, and you get into deep trouble when you try to specify conversions and mixes of types, and it gets trouble. Anyway, we had a merger of these two ideas. It looked good at the time, and it completely failed. And then we went back and started with the concept as predicates, as you've seen here. As in the type T is an input iterator if it has the properties an iterator is supposed to have, and so on. And this became an implementation and a technical implementation, and it works, and several major libraries have been written using it. So again, it takes a long time, and we're going to get it in C++20. Essentially all is in the library. So what is it? Well, basically here's a predicate. A forward iterator T, ask is T a forward iterator? Equality comparable T of U, can T be compared with U using equals and not equals? Still have to invent the syntax for saying this. I'm still going through explaining what things are as opposed to how you write it down. And concepts are fundamental. You should represent fundamental concepts in an application area. They come in clusters, monoid, group, field, and ring. It's just plus and minus and 1 and 0 are not actually totally independent. They relate to each other in certain ways. I mean, if you have plus and minus and then you get multiply, there has to be a relation there. That's where the semantics comes in, and so the operations comes in clusters. Any domain I've looked at, you don't actually have freestanding concepts. People think of single property concept. They start out with saying, let's invent addable. That's something you can use a plus on. Doesn't make sense by itself. Think about subtractable. Doesn't make any sense. Number makes sense in some point. And you can go into the math area and get the hundreds of years, well, 150 years of background of how actually do these in general. Anyway, here in iterators we have input forward, bidirectional, random access operations, and you have iterators that support those. So I set those concepts in the original STL. Yeah, there was those concepts, and it said so in the manual. So basically, we've always had concepts. Every successful generic library, when you write a template, there's something in your head that says what you're requiring. And it's in your head, it's in the comments, it's in the design document, but you didn't tell the compiler because you have no way of telling the compiler. That's bad. So we even had concepts in C. Go back into KNR 1 from 78, and it says an arithmetic type is, and a integral type is, and then the rest of the thing is defined in those terms. What are those? Well, they are concepts. We have the iterators, we have the math, we have the graph concepts. A lot of people have been working defining general graphs with concepts. And now we're getting direct language support, and we have to learn to use it well. So what makes a concept good? I mean, now we're moving from sort of the pure philosophy into what will actually work in practice. The standard says what's legal and what's the notation. It doesn't say what's good. Most code doesn't do anything meaningful, right? If you let the cat walk over the keyboard, you get something. It might be legal, but especially if you have an IDE, but it's not going to be good. The standard just says whether it's right or wrong. Now we have to have some rules here that guides us towards doing it well. And one of the things that comes a lot is people think that you have to have the minimal requirements for everything. The problem is I can't remember the minimal requirements for everything, and I want plug compatibility. So I don't want addable for something that can only add, because then tomorrow I want to use a plus equals. And I didn't say plus equals, so you now changed the requirements. So I want to represent things that make sense, make semantic sense. Like a group of the four arithmetic operators will give you is it an arithmetic or is it an integral? I don't remember. It'll give you one of those. And so such things won't. So for a number, the operations make sense with the usual rules, and has plus, this is suspect. And good concepts support interoperability. That is good. And furthermore, if you invent a lot of little concepts with funny names, I can't remember them. If I invent a lot of concepts with funny names, you can't remember them. So we have to go for fundamentals. So let's see. A concept is not a type of types. If you're thinking in terms of type theory, you would have noticed already that some of my concepts has more than one parameter. That is, something meets a predicate, not just based on one type, but on two. Equal, comparable, takes two arguments. We can handle mixed arithmetic. That is, we can compare things, we can compare a string to a string literal, and that kind of stuff. We can add an integer to a float. Those are two different types, and there has to be a relation between them. We can express it. Basically, there has to be a common type. You can convert the one into the other, or both into the common type. All that can be defined. It's not just homogeneous arithmetic, homogeneous comparison, because if it was, it wouldn't be C or C++. We rely critically on being able to add integers to floating point numbers and things like that, concatenate strings to C-style strings and such. So this is necessary. They are not just types of types. And they are not type classes. If you check on Haskell and something like that, we can see where they differ and also why. I'm not going to go there. There's a paper by me about this you can look at my publication list, go to the section on WG21, standards papers, and there's something about how to do that. I've discussed this with Python Jones and Phil Wadler, who's sort of the ultra gurus in Haskell. It's not the same. It's not meant to be the same, and some of the ideas actually predates the Haskell stuff. And most concepts actually take more than one argument here. Input iterator and assignment comparable. Yeah, that's good. And basically, like templates, complex concepts can take values. So basically, I could define some kind of buffer concept that takes a pair of types and a size, and the t has to be a regular type, and the integer has to be an integer here, and so it requires that b and the size you can get if you use a subscript, you get a t reference. You can write things like that, so you can actually define a buffer as something you can subscript with a subscript type, and it has to yield an element type. That's what that one does. And by the way, the elements have to be regular. Regular basically is like an integer. You can copy them, you can compare them, you can take their address. Nobody has done dirty tricks by redefining equality to mean less than, and things like that. That's what a regular type is. Most of our favorite arithmetic types are regular. There's other concepts like that, but this is just one of them. And so basically they come in clusters. I've said that. Here is an example of how you want plug and play. It is quite common for people who are beginning with generic programming, or even when they have been doing it for a long time and become fanatical about it, they look at this and they say forward iterator, type name, first one, blah, blah. Here, I have to decide whether I'm using plus equals or plus and equals. And if you minimize the requirement from looking at just that, you would say that the requirement here would be that you could plus equal it. Plus equal? Doesn't sound right, right? It should be a regular thing with that has the number properties, probably an integral or something like that. And here I'm returning it. Do I require that it should be copied? Well, it has to be copied or moved. That's the only way that sentence can make sense. So you have to specify this, and you have to generalize it to the point where it makes some sense. Okay, this sounds fairly sort of hot air, but here's an example from a real from a real application. It's almost completely correct. Basically, I want an input channel which takes a transport and a message decoder. Obviously, this is code from a communication system, and actually it is a real system used by my bank. So basically, its input message should be the message adapter for the input buffer. The message callback should be a function that can take an input message. Error call should be a function that can take any operation of that type. And then we take the transport. This is a variadic template that takes the argument and initializes the transport argument. By the way, here is one of the most beautiful examples of variadic templates. I do not know what the transport is because that is a parameter. But I want to store one of them. So this argument, I just give it a bunch of arguments and it tries to initialize it. And if it fails, I didn't have it right. This is nicely typed, fully typed, and I don't have to introduce an intermediate abstraction like initialization format. How would I define an initialization format for a transport when I don't know how transports are made? The user for these knows that transports has certain properties that they can use in their implementation. They do not actually know how to make them. Notice I said the difference between a type and a concept is that a type shows you how to use it, but it doesn't show you how to make them. This is how You slip the arguments in. Now the initialization is done. We have this one. The user of this abstraction here hasn't a clue how to actually initialize it. Sorry, the implementer of this has no clue how you make transports. Good. So let's go look at the design here. This is Gabby. Gabby does race. He's been working with me for better part of 20 years. He is also one of the main designers, probably the key designer of modules. So if you like fast compiles, you can thank him for that also. He works for Microsoft these days, used to work with me in Texas. Yeah. So basically, let's define some concepts. I've been working from the use and why, and let's see what the syntax look like. Okay, a type T is sortable if it is a sequence, if it has random access, and if its value type is comparable. Yeah. Yeah, that's homogeneous here. Otherwise, I would have to have sortable of T comma something. But that's what I've been saying. The only difference is that the compiler understands this stuff. It is still not brain surgery. And second, we can drop one level down. This is defining a concept out of 3 more primitive concepts. How do you get to the bottom of this? Concepts are made out of concepts are made out of. Okay, at some point we have to make it out of something real. So here, a T is equality comparable if you take 2 T's and you can compare them equal, yielding a bool, and you can compare them with not equal, yielding a bool. That's the syntax. That's basically all of the syntax. So here we built them out of other concepts, and here we built primitive concepts out of basically usage patterns. This says that if you take an A and a B and compare them, they have to yield a bool. You can put arbitrary code in there. So here it's T, but if T has to work together with a Q, you can put that into, and you can just write code here that specifies what is required. Concepts, it tells you how to use things. These are the most primitive concepts. It tells you exactly which operations you can do to something, and it will be considered equality comparable. Let's see. Related types, yes. It gets a little bit stickier. Here's the sequence concept, which is pretty fundamental. And so sequence is fundamental, so we're doing it with a requires clause. We're defining it. It says there has to be something called a value type of T, and there has to be something called iterator of T. It just checks that this thing exists, that this predicate is true, whatever it is, this predicate is true, whatever it is. And then there must be a beginning, yielding an iterator, that one, and there has to be an end, has to yield an iterator. And by the way, it requires that there should be such a thing as an input iterator it requires that the iterator of T, which you see up here, should be an input iterator. It's a requires clause, like you saw requires clauses in other cases on functions and such. You can also put it into the definition of concepts. And basically, we want the iterator of T to be the same for the value type and the value type of the iterator. In other words, if it's an iterator that's supposed to point to something, it should point to that same something. And so this can get sticky. The lower you are down in the hierarchy of specifying things, the harder it gets. Fortunately, you look in the standard, the current document, and it'll have the basic ones. You don't have to define sequence or equality comparable. That's been done for you. It's in the standard library. I mean, like if you had to define your own square root function, you had to learn a fair bit about floating points and algorithms. So you don't usually do that. You just say square root of 2. That's something you can ask a student to do on day 2 of a programming course. Using sequence is something you can tell a student to do on a second day of a programming course. Probably not quite the second day, maybe the second week. but asking them to implement this is where it gets a little bit sticky. And just like if you think this is too complicated, try and implement square root or sort or some of the other things we do all the time. There are courses of it in your university undoubtedly. Okay, so defining concepts, you won't get them right the first time. That's one of the observations about all code. So how do you get there? You use a library if you can. That's standard, that's standard, that's standard, that's standard. So go and find them in the standard. That gives you most of the concepts you'll want on the first couple of days. And then one thing we learned along the way is that getting a concept slightly wrong is actually useful, because that means that you can write the thing you think about and you'll get the checking that you asked for. But you very rarely get to ask for everything that you need in the end. So we can start from the beginning. Here is an example. First of all, the people start writing some, and then they try to define some in terms of a requires clause. This is ugly. It requires that this requires clause is met. People have said, why don't you clean up the syntax? I said, I don't want to clean up the syntax. This is fundamentally ugly. You're repeating the code from the implementation. That's just not right. Furthermore, this will only be used here. And when you come and do it in other places, you have to repeat yourself. So it encourages cut and paste. And no, I'm not going to improve the syntax to allow you to write bad constraints and do cut and paste. Now, what you can do is addable here. This is, okay. You don't usually want addable, but let's start from the beginning and get it right. You can always say that you have to be able to add something, and then you can say you'll be able to do some plus equals, and you'll be able to copy it, and you can construct it for 0. This is pretty good. It's better. Now, addable itself is probably not a very useful concept, but going from this kind of mess to this allows you to say, well, if it's addable, think about it, requires, that which is set up there, but there's also these alternatives that you want to be able to add to it. What if I wanted to use plus equals? Once you're defining this and naming it, you'll get it more right. Not perfectly right. I keep forgetting to construct from 0 or some null point or some element like that. It's all right. I'll get the checking for all the rest. And when I get a problem, I can improve the concept. Whoops. Let's see. Accidental match. There's people who worry a lot about, since I'm doing this thing of saying, do you have these properties? And if so, I do it. What if you accidentally match the concepts? You have a type that accidentally have the requirements that I had. Bad things will happen. The standard example here is a concept drawable that requires a draw. This is very primitive, it's just a single property. I'm always suspicious about single property things, because in the real world it's very rare to find something that only have a single operation or a single property. Do they copy or don't they, and things like that. It's small, but anyway, let's do this just to get into trouble, and I'll explain why it's rare. So we have a shape here that draws. I just said it was drawable if it could draw. Unfortunately, I hadn't thought about the cowboy, who can also draw. And so now I say drawable, vector of drawable, for all of them draw. I'm going to get a surprise, because this code meant for shapes, not for cowboys. I mean, cowboy draw, that's it. We don't want that. So basically, there's something wrong here. But it doesn't happen all that often, because we don't actually have these single property things. Look at the iterator hierarchy. Each kind of iterator has half a dozen to a dozen operations, and accidentally matching half a dozen requirements is not likely. It hasn't happened often. So avoid these has plus, has minus things and go for numbers. So here is a thing. When I first did this, I didn't get all of these right the first time. Of course, I remembered plus, minus, star, slash. Did I remember unary minus? Actually, I didn't, but I should have, of course. If you're experienced, you make fewer mistakes. And here, of course, once I can do these, I would like to do those. And here you can initialize it from 0. In the ... we better be able to say it's copyable. I mean, do you want a number that you can't copy? Probably not. If they're big, you better say they're movable too, because you don't want to actually copy matrices when you don't want to. And you can say that here. It's not that hard. Definition checking is another problem people have been talking about. I have talked about all the time about how to use it and how to check usage. One of the things people say, but I want my library code to be checked by the concept checking. And we're not offering that, not yet. We could do it, I believe, but we haven't done it yet. We get a lot of benefits from this. So here is a classical thing. I do a forward iterator, and it looks all right, except forward iterators do not provide +1. They provide ++, but not +1. So here is an error, which I won't find till it is fired for something where you can't do it, like a list. A list's forward iterator does not equal do plus, it only does ++. So we're not trying to do that. That's beyond the current scope of the design. Thanks to some experiment from Gabriel's race, we actually know how to do this if we have to, but it didn't seem worthwhile. The observation is that at least 90% of the benefits of concept checking comes from checking the uses of templates, not from implementing it. So we get some screams from some implementers that want an easier life, but I'd rather help users if I can. Implementers tend to be smarter and have more time. Users are most of us, and it defines it, and we know to do it. And how can you manage the transition? One of the things that not having definition checking does is I can stick things in. I mean, that was a clear bug. But what if I had a piece of code here and I wanted to put some debug information in there or some tracing information in there? Should I change the requirements to say traceable, has debug information and things like that? Or should I just let it use some operations that I haven't defined in my stable interface? I want the stable interface, and if people want to instrument their code by putting good stuff into their generic functions, fine, they can do that. That's the current state. It used to be that we thought we were sure we wanted definition checking. Now, several of the most experienced users of this says, "Oh, they're dead body." If we put template definition checking in, they will be against all of this. So my answer is we want template definition checking if we can figure out how to create escape clauses that allows you to selectively be unchecked. Maybe never. This requires serious work. This, by the way, is radical. If you look at generic programming and the way people have been defining constraint systems, that's not the usual answer. But it works better at scale. Definition checking, let's go there. Using level concept. Here is a way that you can define merge in the standard. It takes 3 types: a forward iterator, another forward iterator, an output iterator. You have to be able to assign things in 2 ways, and you have to be able to compare things. That's copying straight out of the standard. And I probably didn't invent the word headache-inducing, but it is. This is about as complicated as it does. We can do better. Let's define something called mergeable, and then we can say we want 3 types that meets the requirements of mergeable. So we can define the 3-valued predicate. After all, our concept is just a compile time predicate, and we can do that, and we can say, I want it mergeable. And that's the way we tend to write our code. Not there. This is sort of what people do in the first couple of months of programming. They write everything in a linear style. What we do is, of course, we define a function which we use. That's a compile time function, a compile time predicate. We can do some more, but we're not going to do there because they're not allowed it. And there's mergeable. What does it mean to be mergeable? Exactly what I said before. You need 3 types: forward iterator, output iterator, assignable, and comparable. Boom. And now our code looks like that, which is quite manageable. And mergeable, in fact, is used in 4 or 5 places in the standard. So if we had just written things like that, we would have had to repeat this mess about 5 times. And so we are learning how to use this. And one of the strong recommendations is, if you get into something that looks like that, define yourself basically a predicate, a subroutine, and use it. That's what we do in every other area. Okay, principles of concept design. I'm running out of time, so I'm just going to show this, and then we can have Q&A. Let's see. Major inspiration: Stefanoff and McJones' Element of Programming, a very good book. If you're into semi-serious mathematics, you'll love it. If you're not, you may not. That is Alex Stefanoff. That is McJones. They are really nice guys. That is an older version of Bacchus. If you were here in the morning, you saw the younger Bacchus. But he didn't take part in this. He just happened to help inspire these guys, who then in turn inspired me and others to do this work. Basically, we have to raise the importance of semantics and in the representations of things, and we want to distinguish between ad hoc and universal. Universal are the concepts, ad hoc are the requirements clauses. And we want to make a consistent set of properties as concepts. That's what the standard library things are. Things like input iterator and regular and stuff. And we, yes, want to do that. So I think I will stop here because I've been ranting on for a bit too long. Maybe I should blame that lunch again. Yeah, we can probably use the time better for Q&A, so thanks.
So thank you. Now,
yeah.
Thank you very much, and now we have the first question here.
Thank you very much for teaching us. I was thinking throughout your presentation about TBB. In TBB you have this parallel for, parallel reduce, and one of the arguments is a functor. So you need a function, an object that belongs to a class that overrides the operator parentheses. And if I were to define a concept for that, it only requires a T of the class T that has T parentheses, or is this too simple?
You could start by defining that it has to be derived from the class you already had. You can say that. Requires derived from. Mm-hmm. Or you could simply set the operations that you require and then leave it up to the user to whether he would get those properties by deriving from your original class or not. We have several cases where older design had a hierarchy, and then we took away the hierarchy. That is, instead of saying there's a root to this hierarchy and everybody has to derive from it, we just take the definition of the base class and fracture it out and says, well, You must be able to draw, rotate, and the other things. And then I don't care how you get me that one, just as long as I can get the operations. And so sometimes you can reduce the binding in the thing by not having the base class. You have a choice.
But there is not a basic concept already in the library for a functor.
There is a concept for a functor, yes.
Okay.
It's in the it's there.
In fact, I think there is more than one, but because a predicate is
Yeah,
another
predicate
kind of
is
functor.
another one. Predicate, functor, homogeneous function, the usual. They're there.
Hi, I have a couple of questions, if I may. The first one is, what is the thing that you missed the most from the first specification of concepts that failed to make it into the C++ 11 standard? And do you think it is feasible that the current specification might evolve to cover these things that you missed from this initial specification?
Currently, what has gone into the library is anything to do with ranges and algorithms. So there's about 100 standard algorithms. They will be defined in terms of concepts, and they are, and the concepts used for that are there in the standard. I believe that the standard containers have not been rephrased in terms of concepts. So when you say a vector of t, t is still a type. That will have to be done. And basically, our experience from C++ OX, where the definition of concepts failed, was that we could specify everything in the standard library that is generic in terms of concepts. We just don't have it for C++ 20 yet, but all of the algorithms is a big deal. We used to have random, all the random numbers defined that way, but I don't know if they are making it into 20.
And my second question has to do with definition checking. I don't even see how definition checking might be a desirable thing. And let me explain this a bit. You have an example there where you use a so-called input transport, and you construct the input transport without knowing really how you construct that, by using a perfect forwarding constructor, etc. If you had definition checking there, the compiler would say you have not even specified how the thing is constructed. So I don't see how definition checking might be enforced, because you might use some...
Okay, we have what I usually call a violent agreement. That is, both of us will scream in the same direction. Now, the reason I have this example is that there are lots and lots of people taking really fancy courses in type theory and such, who absolutely know that definition checking is necessary for the system to be sound. And so, for the benefit of those guys, I explained some reasons why we're not doing it yet, and why, if we're going to go there, we need serious research and experimentation.
Okay. Thank you.
It's doctrine in some places, and so when I have to say no, I actually have to say no. I can't just be quiet.
First of all, good afternoon, and thanks for coming to this conference. I have just a couple of questions. People like me are trying to make the transition to data science field, and most of the problems we face nowadays is whether the programming language we have to use, either R, Python, or even MATLAB. Is there the time we can talk about transitioning to C++ to make the transition to data science correctly? That's the first question. The second one is, can we get some copy of this?
Sure.
Because some things I have not so much clue of.
Of course. This was a sort of fairly...
Thank you so much in advance for the reply.
Yeah. So the second one, yes, you'll get the slides. I don't know if you recorded this one.
Yes, we are recording.
So you'll get another chance. And it was a talk about not totally concrete things. It was about why facilities are the way they are and how you might use them. And the assumption is it'll give you some ideas of how you might go about doing it. I didn't quite understand your first question about transitions between languages. Did you mean how do you call C++ from Python, or do you mean, okay.
Since, for example, I'm learning concepts of data science. The first time I get into this field was with MATLAB, because I'm doing the PhD here in this university. But when I was facing to use Python or RStudio, because some companies demand you to dominate them, I was thinking about what if I do it with C++ instead. Is that factible?
Yes, it's possible. It may not be the right thing to do. First of all, TensorFlow is C++, so it's all C++. And there are ways of using it directly. But for experimentation, quick run over a small data set, then run over another small data set, a dynamic language can be quite useful. Now, whenever I want to scale, so I have a bunch of astronomers doing this kind of stuff with Python, and then when they're having to look, instead of looking at some test data, they actually want to look at a chunk of the sky, they translate into C++. So one way of looking at this is look at the requirements for scale. How large data sets do you want to handle? How fast do you need to handle it? And then when you run out of juice in the languages that are easier to manipulate with, R and Python, then you can convert to use the C++ directly instead of using it through Python and R, which you have been doing by then. Now, for a lot of examples, especially smaller examples, and especially examples that aren't really life critical, you never hit that point. And so the problem comes when your output becomes safety critical, or it has to scale to a huge amount of work. I've heard of people using MATLAB and taking 3 months to run an experiment. It was actually my son. He cut it down to half an hour. I mean, you're talking about that kind of magnitude you can get, and I think you'll know when you hit it, because it hurts.
Hi, thank you for this day and these talks. I want to know, you said that concepts are already implemented in GCC and is a start to implement in Silang, and in Microsoft compiler it will be in C++20?
They are in GCC, and it's the technical specification version that's there, so you don't have to litter your code with autos. So they have to degrade their implementation to require auto everywhere. I'm not looking forward to that. Clang is starting. There is a complete implementation, but it's not in the trunk yet. And Microsoft has started. The main designer of some of this is at Microsoft, so we're going to get it. Will we get it this year? I don't know. I hope so. I have reason to hope so.
Okay, if I may, another question. I want to know if you have something to deprecate in the next releases. For example, in C++ 17, I think, you deprecate the register to don't use it anymore. You have any more something?
My experience over the years is that deprecations are very hard and very often doesn't work. We'll see if register sticks. I hope it will go for good, but we'll see. It's amazing how much old code there are. People want new fancy features, they want a simpler language, and whatever we do, don't break my code. And so don't get your hope up. Most attempts to deprecate things have failed.
More questions?
Thank you very much for the talk. My question is regarding allocators, current standard allocators. So current design is a little bit faulty, partly because the lack of composability. So could these concepts help in order to improve this allocator design?
I haven't tried, so I don't know. In general, if you have an interface and you have a type in that interface, a generic type in that interface, concept should help. Allocators tend to be at a fairly low level. They deal with raw memory. And so there's a conversion going on there from raw memory to something. But that's not really a concept thing, because it has to, something can be anything in most cases. So this would not be the first place I would look for use, because the places where we don't need the type information is sort of that. Allocators is one example. There's a horrible type hack inside the implementation of a standard allocator that could be improved, but it's one line, and nobody's going to notice. And the other thing is AST manipulation, abstract syntax tree manipulations, where mostly it just works with an AST of whatever type it is, and there's not much gain. Just about everything else, there's significant gain.
Any more questions? Oh.
First of all, thank you for the talk. This is just a very short question. Is all the concepts system, is it entirely done at compile time, or does it have some part that is done at runtime? Thank you.
There's no runtime aspect there. It's all done at compile time. It basically gives you type safety and better expressibility, better overload resolution, better error messages, and it does not. Runs exactly as fast as the untyped version, and the surprise comes when the fact that it helps at compile time. We know there's zero overhead at runtime. That's inherent.
Okay, thank you.
And by the way, other concept systems or type trait systems or type class systems have runtime overheads because they use indirections and functions. We don't do that. It's all compile time predicates.
Thanks again for the talk. I wanted to ask if when the compiler detects that one concept is not met, if it tells you all the concepts that are not met at once in that same compilation, or it just tells you the first one, you run again, tells you the second one that is not met?
Error messages are a dark art, and you can do it either way. That is, you could find an error and then carry on and see if you hit any other errors. And the other thing you can do, you can either say it, okay, if I try to sort an integer, there's two things you can do. You can say an int isn't sortable. That's the first level of thing, and I love that. And currently they are very keen on saying int isn't sortable because int does not supply beginner end or something like that. And that tends to be a bit longer once the compiler writers get into it and you get to more realistic examples. So the first is a one-liner, and the second is maybe a 5 or a 10-liner. I have recommended, and I don't think anybody listened, that they should default to the short version so that people who wanted more information should just flip a switch for verbose. And the reason is, once you understand what concept you're using in your application, just telling it that it's an integer and it's not sortable is all you want to know, and then you don't get these cascades. Furthermore, for having done one sort of line of code, like sort of one, there's no reason why you don't carry on and look for other errors below. And as usual, if you can get cascading errors, so you don't carry on for whatever, but it's much as usual. But people that are writing test cases don't assume you understand your concepts, and so they want all the information. And they haven't learned yet that once we get used to things, we don't want all that detail.
Any other question? Well, then, just let's thank again.
Thank you.
Bjarne.
Thank you.